So this week I'm very happy to introduce Juan Maldacena. He probably doesn't need much of an introduction because I think many people know of his enormous breakthroughs in string theory and fundamental physics. So I'm not going to give him a long introduction, but he's a member of the Institute for Advanced Study. We tried to get him a couple of times in the last couple of years, and I think once it almost happened, but he was sick or something. So I mean, it's been a long path to get him here, but he's one of the people who it's easier to get remotely than in person. So we're very glad that we finally managed to tie him down and get a talk from Juan, because we've been looking forward to this for years. So Juan, it's all yours. Take it away.
Okay, well, thank you. Thanks for the introduction. And yeah, usually giving a talk with Zoom is not the same, but one of the things you miss is people asking questions during the talk, or at least saying where they are following your talk. So if you really have a question, please interrupt me and ask the question, because it makes it really more enjoyable to me. So black holes have been in the news recently, so through gravity wave observations and through the Event Horizon Telescope, or through observations of stars near the center of the Milky Way. But I will not talk about these black holes. I will mainly talk about quantum aspects of black holes. So for discussing these black holes, where new observational results have been found, the classical general relativity is good enough. But we'll try to go beyond that and ask about quantum aspects of black holes. And more in particular, we will be discussing aspects of the black hole information problem. And what I will talk about is mainly contained in a review that we wrote with these authors. And it's based on two important papers that came out in 2019 and several follow-up papers. And recently there was another interesting development on the black hole information paradox that I will not review. So a series of papers by Shankar and Stanford. So the outline of the talk is the following. First, I will remind you that the entropy of black holes is equal to the area of the horizon. Then we'll introduce a new formula for the entropy of black holes, for the so-called fine-grained gravitational entropy. We'll discuss what that is. And the entropy will be also given by a type of area formula. And then we'll compute the entropy of radiation coming out of black holes using this type of formulas, and get a result which is consistent with information conservation as opposed to information loss. So that's the outline of the talk. And the talk will not be historical, but hopefully will be pedagogical. So first, we start from the black hole. So this is the metric of the black hole as seen from the outside. So when R is bigger than Rs, we are in the outside region of the black hole. R equal to Rs is the black hole horizon, where the time component of the metric goes to 0. And this value Rs is the Schwarzschild radius of the black hole, and it's given by, it's proportional to the mass of the black hole. Now, the most important result about quantum aspects of quantum black holes is that black holes are hot and have a temperature. So in other words, Hawking radiation. So black holes emit radiation at a temperature given by this formula. I will give a derivation of the formula in just a second. But this is very surprising. It's very surprising because this effect implies that you can have white black holes. Now, as a little quiz for the audience, I will ask you, how big is a white black hole? You can think about this for a couple of seconds. The temperature is given by a formula. Here is the formula, the temperature in terms of the size. So you have to figure out the temperature of white light and figure out the size. Well, I mean, this formula is saying that the wavelength of the emitted light is proportional to the size of the black hole. So if you want it to be white, it has to be of a size comparable to the wavelength of white light. So roughly speaking, the size of a bacterium. It would be a pretty heavy black hole. It would weigh about the mass of a continent. And it wouldn't be emitting too much radiation. So something like a microwatt or so. but it would be visible with your naked eye. So you can have a white black hole. So this effect is so surprising that even the name black hole was incorrect for black holes. But we still call them black holes. Don't worry about that. Okay, so this is, in order to talk about the derivation of the temperature, I'll remind you of some things, of a connection between temperature and circles in Euclidean time. So first, let me remind you of the thermal partition function for quantum systems. So if you have statistical physics, you calculate the the partition function of statistical mechanics. And that's computed by taking the trace of e to the minus beta h, or summing e to the minus beta times the energy for all the states you have in your system. So this is a formula both, let's say, in classical and quantum mechanics. Here I wrote the more quantum mechanical formula. Now, an interesting thing is that you can view this formula as evolution in Euclidean time over a circle of length beta. So beta is the inverse temperature. And why is that? Well, if we had e to the ith, that would be ordinary Lorentzian evolution. So instead of having an I here, we have no I. So that's the same as going to Euclidean time. And the trace is like identifying the beginning and the end of that evolution. And so that's the same as considering the theory on a circle, on a Euclidean circle of length beta. Okay, so this is just some observation that has nothing to do with black holes. So this is true for any system. Could be a qubit, it could be harmonic oscillator, it could be any system that you have. Okay, so now we go back to black holes, and we had the metric of the Lorentzian black hole. So that was the metric that we had. And then we go to Euclidean time. So we make t to I times the Euclidean time. So that, in effect, changes the sign. Yeah, please. Is there a question? No? OK. So now the metric is a completely Euclidean signature metric. And let us focus on the first two dimensions, so the radial direction and the time dimension. And what we see is that we have that this dimension shrinks to 0 at Rs equal to R. But in these two dimensions, it is possible for a dimension to shrink to 0 in a smooth way, if this circle is compact. Okay, so if we really have a circle as opposed to a non-compact direction. So we identify the Euclidean time with some period that, based on the previous discussion, we are going to interpret as the temperature. And we interpret it that way because when we are far away in the region where R is much bigger than Rs, this would be just simply a circle, a Euclidean time circle. And as we discussed before, when we consider a theory in Euclidean time with a compact circle, it can have the interpretation as considering the theory at finite temperature. So we're considering the space at finite temperature. And it turns out that if you adjust this temperature appropriately, then the space is completely smooth at R equal to Rs. So at where the horizon was in the Lorentzian signature, now it becomes like the origin of flat space. And the full geometry of these two dimensions, so the circle dimension, Euclidean time, and the radial direction, looks like a cigar. So it has a constant size circle far away, and then the circle shrinks to 0 at where the horizon was in the Lorentzian signature. So we can think of this. So here we see that in order for the geometry to be completely smooth, we need to adjust the temperature. And when you work out what that adjustment needs to be, so you can get that from looking at the details of this metric. I will not go over those details, but you find that beta is proportional to Rs. And this formula is not too surprising, given that Rs is the only scale that appears in this metric. So it has to be proportional to Rs. So working out the 4 pi is a little more work, but not too difficult. So we are going to interpret this. So this solution is interpreted as a black hole in thermal equilibrium. with a gas here, well, in a system at temperature beta. So this is saying that the black hole of precisely this size, where we have this relationship between the size of the black hole and the temperature, is in thermal equilibrium, so therefore the black hole has this temperature. Now, once you know this formula for, well, this formula was derived in this way by Gibbons and Hawking. Hawking had derived the formula previously in another, perhaps more direct but more complicated way, more complicated, let's say, to explain. But once you have the formula for the temperature, you can calculate the entropy. So you do that in the following way. So you know, in general, you have the first law of thermodynamics, which says that the small variation in the entropy is related to a small variation in the energy divided by the temperature. Now, the energy is equal to the mass of the black hole. So that's the formula E equal to mc squared. Here, mc is 1 in most formulas. And we have the temperature is a function of the mass, so we can integrate this formula. And when we do that, we find that the entropy has a simple expression in terms of the area of the black hole horizon. Let me go back to define the concept of the area of the horizon. So here we had discussed the Euclidean black hole geometry, and now at each point, so here we discussed only 2 of the dimensions. There is also a 2-dimensional sphere. So these are the angular directions around the black hole. And the sphere, of course, grows as we go to larger values of r. But it acquires a minimum size at the horizon, where the size is just the radius of the sphere is this quantity rs. So that's what we get here. And so it's the area in Planck units. Here there are factors of h bar and c that I have not included, and the Boltzmann constant and so on. But when you work it out, you find that it's the area in units of L Planck. And L Planck works out to be a length of order 10 to the minus 33 centimeters. And this is the length scale at which quantum gravity effects become important. So for a big macroscopic black hole, this entropy is very, very, very large. It's much larger than the entropy of any system of a similar size. In fact, in our own universe, the entropy, if you calculate the entropy of everything that exists in the universe, you can calculate the entropy of the cosmic microwave background, the entropy of the matter in the stars, and so on. And you should also calculate the entropy of the black holes. So there are entropies of black holes whose size is stellar mass, and there are the entropies of supermassive black holes. And the entropy of the universe is dominated by the entropies of the supermassive black holes, like the one we saw, whose picture we saw in the first transparency, the one in the center of M87. Okay, but what we're going to learn from this is that the black hole is a thermodynamic object, and this is rather surprising. So we'll now discuss in more detail the geometry of a black hole. So now we go back to Lorentzian signature, and we'll be drawing certain diagrams, which are called Penrose diagrams. And we are going to ignore the directions of the sphere. So we are never going to draw the sphere dimensions. We're going to draw just the time and space direction. So the radial direction, so the radial and time direction. The radial direction goes horizontal in this figure, and the time direction goes in the vertical direction. And then we're going to deform the geometry in such a way that we keep the angles fixed. In particular, the directions of light rays will be at 45 degrees. So in this figure, if you have a light ray going into the black hole, it will be a light ray going in this direction. A light ray coming out of the black hole is going in that direction. This region out here corresponds to the region at infinity that we brought to a finite location by doing a stretching transformation that preserves the angles, as we said. And this geometry represents the collapse of a star. So we start having a star that has some size, and it's collapsing. So this r equal to 0, this is the center of the star is here. Here, the sphere that we're not drawing shrinks to 0 size in a smooth way. And at some point, we have light rays. So sorry. As the star collapses, we develop a singularity here in the future. The metric outside the metric in the white region, so outside the star, is given by the Schwarzschild metric that we wrote before. So that's this region here, and that can be continued also to the interior. The horizon itself is where the time component of the metric shrinks to 0 size, is a completely smooth place, which you can cross without feeling anything special. But that surface is actually not a point, but it's actually, or even a two-dimensional surface. It's really a three-dimensional surface. So there are two directions along the sphere, and then there is this direction, which is along. This represents the trajectories of light rays that are about to come out of the black hole, but never quite manage to come out of the black hole. So a light ray that starts a little previously will be able to make it out to infinity. A light ray that comes out from here will go into the singularity and will not be able to escape to infinity. So the horizon is just the trajectories of light rays that separate the region which is accessible from the outside from the region that is not. Okay, so that's the geometry of a collapsing black hole. It was found in the 1930s. Notice in particular that the area of the horizon is here constant, that's what happens in the Schwarzschild metric. But here it's increasing from 0 size. It increases to this maximal size. Yeah, in fact, it was found that the areas of horizons can only increase. So if you have black hole collisions, or you have any process, you throw matter into a black hole, etc., classically, the area of the horizon always increases. And it turns out that, so this was a theorem that was derived from the point of view of general relativity, but then it got reinterpreted as the second law of thermodynamics, of black hole thermodynamics. So has this interesting interpretation that now, if the black hole normally can have some matter outside, so we normally define the total entropy of the system out of the black hole as seen from the outside as given by the area plus the matter outside. In fact, that was the original formula that Bekenstein proposed in the 70s for the black hole entropy. So, I mean, he knew about this term, but he added the area term. So this combination is particularly nice for the following reason. So let's ask a question. Imagine that the black hole emits Hawking radiation, so it will lose energy, and its area would become smaller. Now, what happens to the entropy? So from the point of view of the second law of thermodynamics, we would expect the entropy to increase. But what happens is that the area becomes smaller, but the matter entropy, which should also include the entropy of the Hawking radiation that is being emitted, will increase. Okay. So one lesson is that we also need to include the entropy of quantum fields here, and the so that should also be included in the formula for the entropy. Now, these results have inspired a very influential hypothesis in the study of quantum aspects of black holes that we called it a central dogma in the study of quantum aspects of black holes. And the idea is the following, is that the black hole can be viewed as a quantum system. In other words, if you have a black hole and you do experiments only from the outside, so maybe you throw some matter into the black hole and you watch the black hole evaporate, and any kind of process that you can define from the outside, you can study those processes. And the idea is that for the purposes of studying those processes, you could replace the black hole by a quantum system that has s degrees of freedom. So has a number of degrees of freedom, or qubits, equal to the area. Okay. And furthermore, those degrees of freedom evolve according to unitary evolution, as seen from the outside. So the idea is that no matter what happens inside the black hole and so on, we can think of the system in terms of those degrees of freedom. So in other words, we can sort of cut the space-time sort of around the black hole, and So you take, and then everything that is within this this imaginary cut that we do in the spacetime, we replace the spacetime and the black hole and everything inside by some system of qubits. So some quantum system, some mysterious qubits. This dogma doesn't tell you what those qubits are, only that they exist and that they evolve according to unitary evolution. Okay, that any process that you can imagine doing with a black hole will have could be understood in terms of a quantum system of this kind. And returning to the thermodynamics, so we said that we could interpret the Euclidean black hole in terms of the thermodynamics. So so this calculation is a calculation, so we can calculate the action, the gravitational action of this geometry. That's I gravity, so that's the gravitational action for this geometry. And the idea is that this is supposed to give us the partition function over the sum of those mysterious degrees of freedom that we haven't defined precisely. So, so the evidence for this, so there is now some evidence for this. This hypothesis was made somehow before this evidence was found, but there is more evidence through some string theory results. So for very special black holes in special supersymmetric theories, you can actually you can count the microstates using some special string theory techniques, and you reproduce the area formulas. And not only that, but you also reproduce corrections to these formulas. There is also the so-called ADS-CFT correspondence that tells you that if you put that cutoff surface, if you have a black hole in a certain negatively curved space called anti-de Sitter space, you don't need to know the details of what that is, and you put that cutoff surface very far away near the boundary, you can replace the black hole and the whole space that exists inside here by a system of qubits, of very strongly interacting particles that live at the boundary of this space. And so the black hole becomes a very strongly interacting fluid, a hot fluid in that system of particles. Okay, so there is this evidence in favor. I mean, this is a conjecture, but it's a conjecture similar to the central dogma, except that here we say exactly what the degrees of freedom are, at least for some very special theories. On the other hand, in 1976, Hawking said that this cannot possibly be true. So he gave an argument against that central dogma. And his argument came from looking at the geometry of an evaporating black hole that was made from collapse. So this is a same type of diagram that we had before, except that now we take into account the effects of black hole evaporation. So black hole evaporation takes place by producing particles. So this is, for example, and producing pairs of particles. There is one particle that is produced and goes to infinity. Another particle is produced and goes into the interior. And these two particles, the two red particles, are entangled with each other. The two green particles are entangled with each other, and so on. And as these particles get emitted, they will reduce the mass of the black hole until eventually the black hole disappears completely. We don't know exactly what happens here, but not much entropy and so on is emitted at this final point because there isn't much entropy left over. And then we go back to flat space, and this top part is the Penrose diagram. That is the diagram of flat space. Now, if we look at the full quantum state on these spatial slices, so this is at some particular time slice, we have a pure quantum state here. Let's say the star was in a pure state, so we have a pure state. Here also, it's in a pure state. We have entangled particles here, but they are in a pure state. But if we consider only the slice here in the far future, we are capturing only one member of these Hawking radiation particles, and we are not capturing the member that is in the interior, so the other member of the pair. And since these pairs were entangled with each other, there is a non-zero entropy that we get here at the very end. If we were to consider both the outside and the inside, then we would get that the entropy is zero. But naively, the inside is inaccessible to the observer outside. So Hawking said, well, the observer outside only sees these particles, and therefore the entropy should increase outside. Now, this is another view of the same thing. So you can view this Penrose diagram as, roughly speaking, the following. You start with some matter that is in a pure state, and you produce two kind of separate universes. So one is the big universe where the black hole existed, and the other one is some funny universe that ends up with the singularity, which is related to the black hole interior. So we're kind of disconnecting here the two, and they somehow get disconnected at the very end of the evaporation. And one universe contains one of the members of the Hawking pair, and the other universe contains the other member. So you can view this as a very complicated system where you where you split some kind of, sometimes they call these baby universes where they are small, but here they're not particularly small. This could be very big. So we call them a teenage universe. And also it's a kind of teenage universe that creates some problems for the parent universe. So now Hawking said, well, the skeptics would say, well, you started with you have a pure state if you include both universes, but not if you look at only the original universe. And so it's not very different from an ordinary EPR pair where you create entangled particles and you only look at one of them. Now you can quantify this rise of the entropy of Hawking radiation by in the following way. So you can calculate the entropy of the radiation that comes out of the black hole, and you see that it rises monotonically. It's not a straight line, but it rises monotonically. On the other hand, the thermodynamic entropy of the black hole, the area of the black hole horizon, decreases until it goes to zero when the black hole evaporates completely. Again, it's not a straight curve, depends on the details and so on, but it's monotonically decreasing. And there will be a time during the evolution of the black hole where these cross. Now, why is this significant? Well, it's significant for the following reason. So here, this initial rise of the entropy of Hawking radiation is not in contradiction with that central dogma yet, because it could be that this radiation is entangled with the degrees of freedom that remain in the black hole. Okay. However, when we are in a point like this here, the entropy of the radiation at this point is bigger than the entropy of the black hole that remains. So it cannot possibly be entangled with the remaining black hole. It must be entangled with something else if it is entangled with something else. But the central dogma tells us that we can forget about the whole black hole interior and replace that by just simply a system with this number of degrees of freedom at this time. And therefore, we have a contradiction with that central dogma at this time. We don't have to wait till the black hole evaporates completely, where there is something we don't understand at the end point of the evaporation, where we cannot apply the general relativity equations because the black hole is very small and the curvatures are very large. The problem arises somewhere in the middle. It's not exactly the middle, but it's when these two lines cross. At this time, the black hole could be very big. So now the correct entropy of the radiation should be no larger than this purple curve here. So it could be equal to the Hawking radiation here, but at this point it has to become smaller or equal to the thermodynamic entropy of the black hole, okay, or the area of the horizon. So this is the curve we want to find, and the question is, how do we reproduce this curve from some calculation in gravity? So the purple curve is what we expect if that central dogma or unitarity is obeyed. Now, there were other apparent paradoxes with the black hole entropy formula, or just the interpretation of the entropy formula. And I briefly will mention them. First is the full Schwarzschild solution. So the Schwarzschild solution contains the exterior region, which is the one whose metric we discussed in the very beginning. But if you analytically continue this solution, you have a second exterior region, which looks the same as the first, and the two are connected. They're connected. I mean, for example, the geometry of this blue surface here, that's a surface at a given instant of time. It looks like a three-dimensional space that is joined to another three-dimensional space through this neck. And this point here is the waist here of this neck, the smallest area sphere here. Now, this is a perfectly valid geometry. It's a solution of Einstein's equations with no matter. But it's a weird geometry. And you can ask what is the understanding of the entropy in the situation. Now there was another puzzling geometry, which was basically the same as this one, except that we replace the geometry here on the left. Instead of taking it to be an infinite universe, we take it to be a closed universe. So in this case, we have some three-dimensional space here, where there is. So this is the there is one point I forgot to mention. We can we can view this geometry as follows. So we can think of this particular geometry as some initial condition, and then this evolves forwards in time, and then part of it collapses to the singularity, and part looks like the geometry of the exterior of a black hole. So we have two black hole exteriors that are sharing a single interior. So in terms of initial conditions, you can replace this by a closed universe. And so now it will look like a black hole, and where behind the horizon there is a very big universe which can have lots of entropy inside. So we can add some matter here, and we can have a huge amount of entropy bigger than the area. So these geometries were proposed as a counterexample to the statement that the area entropy counts the entropy inside, or the entropy in the interior. So this also seems to be a bit puzzling, and perhaps might look at first sight that is in contradiction with the central dogma. So we'll see how to resolve some of these confusions. And most of these confusions involve the black hole interior. And some of them involve computations of the so-called fine-grained entropy, not the thermodynamic entropy, and we'll see what the distinction between these two is. And the confusions also involve entanglement. So first, we'll have to go back to basics. And remember that the central hypothesis only talks about the black hole as seen from the outside. It makes no claim about the interior. Okay, we'll make a claim about the interior later. So let's first consider this geometry, which, as we said, contains two black holes. There's a minor modification of that geometry where the two black holes live in the same universe and are sharing the interior. And in this case, we can think of, we can apply that central dogma separately to each of the two black holes. And so each of the black holes can be replaced by a quantum system. And the idea is that each quantum system is, these two quantum systems could be entangled with each other. And the idea is that if they are entangled with each other in a very particular state, which has this thermal looping form, so you take all the energy eigenstates of one system and you entangle them with the energy eigenstates of the other system. Then if you take this particular state, the idea is that this particular entangled state is describing a pair of black holes that are connected through the interior. So you get the geometric connection, or sometimes called Einstein-Rosen bridge, from EPR type correlations, Einstein-Podolsky-Rosen correlations. Now, the rest of the paradoxes involve understanding of the fine-grained entropy. And so I remind you, this is something rather general. So there are two notions of entropy that we normally use. One is the so-called coarse grain or thermodynamic entropy, and it obeys the second law. And somehow it arises a little bit from sloppiness, from the fact that you only look at a subset of the observables. And the other is the so-called fine-grained entropy or von Neumann entropy or quantum entropy. And this one remains constant under unitary time evolution. This is, in some cases, it's sometimes called entanglement entropy, but these other names are a little better. And given a density matrix of the system, the quantum density matrix is defined through this formula. Okay. Now, to understand the distinction between the two, perhaps it's better to give an example. So imagine you have a room and you take all the gas in, so you have the gas in the room, it's concentrated on a very small bottle, okay? And it will have some entropy there. And now you just open the bottle, right? So everything is enclosed with this room, everything is evolving unitarily. The von Neumann entropy will not change, but the thermodynamic entropy will increase because there is more available volume. It will become larger. What that is physically saying is that the gas in the room after you open the bottle and it's spread out, it is in a somewhat special state of relatively low entropy compared to the maximum entropy that gas could have. And the coarse-grained entropy just computes that maximum entropy could have. Now, for the moment, we will be talking about the entropy of the black hole as seen from the outside. So that's what we are computing. And this is the entropy of the quantum system that appeared in our central hypothesis. Okay, so that's what we are going to be computing. Now, the first observation is that the area of the horizon computes the thermodynamic entropy. And one way to understand that is that we saw in the collapse geometry that when the black hole was collapsing, the area of the horizon increased, right? But the process of collapse is a unitary process, and therefore the entropy should not change dramatically. Okay, should not change. I mean, there is a little bit of Hawking radiation emitted, but that's a small amount, so the entropy should not have changed. Okay, therefore, if it was the von Neumann entropy, it shouldn't have changed. So the area of the horizon behaves more like the thermodynamic entropy, which is the entropy that obeys the second law of thermodynamics. Now, it's surprising that there is another formula that computes the fine-grained gravitational entropy. And it's a formula which is rather similar to the black hole entropy formula. The only difference is that you compute the area of a different surface. Okay, that's the only difference. And you have to find this other surface, and the procedure is slightly in bold. Well, not very in bold, but the first time you hear about it, looks a little funny. So the idea is the following. So you imagine we are going to try to find the surface. So we make an ansatz. We say that maybe the surface is here. Let's say a trial surface here. Remember that a point on this diagram is a surface in the four-dimensional space-time. So there is the surface, and then there is the region outside the surface. So we compute the area of the surface and the entropy that is contained on this spatial slice, the entropy of the fields on this slice, or the quantum fields, or the classical matter, or whatever you have here outside. Once we find that, then we start moving the surface, and we find the minimum in the space direction and the maximum in the time direction. So we make an extremum. So we find a point where the surface is an extremum, where it doesn't change if we move it space or we move it in time. Okay. So that minimum will be somewhere. Might be in the interior, might be outside, might be various places. And if we find many of such minima, we choose the minimum, the one that has the minimum combined generalized entropy. Okay. The important point compared to the previous discussion is that we are allowed to take this point inside. Now, you should be surprised by the claim that there is a formula for the fine-grained entropy. This doesn't happen for ordinary, let's say, thermodynamic systems or fluids or anything like that. So, but it does happen when we think about the quantum system that describes a black hole, or when we think about gravity. So let me show you some examples about this. So let's discuss the collapsing black hole, the same example we had before. And let's compute the entropy at this time. So we are going to compute the entropy at this time, at the time after the black hole collapsed. Okay. If we do that, then we see that we can take the surface, we can shrink it all the way to 0 here. And in this case, the entropy that we compute will have no contribution from the area, because it would be 0. And it might have some contribution from the entropy of the star. So the fine-grained entropy will be just the entropy of the star. And this should be contrasted with the area of the horizon, which at this time, the area of the horizon is very big. It's just the area of the final horizon. And as you remember, it was increasing from 0 to some finite value here. So here we see an example where the two entropies are different. And this fine-grained entropy is what we expect that it should have been. So the entropy of the star before it collapsed, the collapse is a unitary process. The entropy ends up being the same thing. Now, the important result of the last few years is to realize that these cases of evaporating black holes, there is actually a second quantum extremal surface, so a second candidate surface that we could consider for calculating the entropy. I will not explain the details of how it's found because the details are a little involved, but the important point is that the area of the horizon is not changing. The area of the surface is not changing very much when you are close to the horizon. And so the entropy of the quantum fields could be quite significant, and you actually find a minimum or an extremum of that combination of the area plus the entropy. I will not perhaps explain all the details. And so we have now two quantum extremal surfaces. So one that, and for all times, we have two of them. So one is the one where we include everything. So we go all the way to the point where the surface shrinks, and we can define that at any time through the evolution of the black hole. And if we did that and we computed the entropy of the black hole, the entropy contained here, it will give us a rising formula. And the rising result for that entropy comes from all the entropy of these pairs of Hawking radiation. So as we emit Hawking radiation, there are the partners of Hawking radiation that are in here that are contributing a lot to the entropy, and they, after a long time, they sum up to a large entropy. On the other hand, there is the thermodynamic entropy of the black hole, which would be decreasing. Okay. On the other hand, we also have the entropy of this other quantum extremal surface, which turns out to be very close to the area of the horizon and gives us an entropy which is decreasing and similar to the area of the horizon. And we're instructed to pick always the minimum of the two. And so we pick the minimum of the two, and we get a result which is consistent with the central dogma for black holes, and so on, for the entropy of black holes. Okay? By picking the minimum of these two contributions. So at early times in this region, the minimum will involve the surface that goes all the way to the center of the geometry, to the r = 0 point. And at later times, we'll have this other surface that is close to the surface area of the horizon. So we get the curve that looks like the page curve for the black hole. But what we really wanted was the page curve for the radiation. So we wanted to be computing the entropy of the radiation, not the entropy of the black hole. Okay, but this is a good start, and I think this is the once you get this, getting the other one is relatively simple. Now the radiation lives in a region where quantum gravity effects look like they should be very small. It could have left if the black hole was in ADS, it could have left the ADS space, or it could be collected in a computer, in a quantum computer that is far away. And so naively, we would think that it's straightforward to compute this entropy. However, we obtain the state using gravity. So we obtain the state for those fields, or those qubits, using gravity. And we should apply the gravitational fine-grained entropy formula for calculating that entropy. And so, in other words, we have the black hole here, this region that naively is inside this cutoff surface that divided the region between the black hole degrees of freedom and the rest. And then we have some surface outside, and that's where the radiation lives. So we are trying to compute the entropy of radiation. Okay. Now, if we imagine applying this formula, then we are instructed to consider possible surfaces. And the possible surfaces here that we can have are surfaces where we include part of the interior in the computation of the entropy here. Now, why would it be convenient to do this? Well, it would be convenient because there is a large amount of entropy here due to the Hawking radiation. And if we were to include the interior, we would reduce the entropy because the partners, we would include both the partners and the Hawking radiation, and so the entropy of those would be reduced. We would pay a price due to the area of the surface. So depending on how big the entropy of the quantum fields is here, it might or might not be convenient to pay that price. So, so we can do this, and when we do this, then if the initial matter state is pure, then the quantum extremal surfaces are the same as the ones we discussed before. So, then we get exactly the same curve that we had for the black hole. So we reproduce the page curve, the result that is consistent with unitarity, by using a formula that we got from gravity. Now, here's the skeptic's complaint. So if you were someone who didn't believe in unitarity for black holes, you would just say the following. This is just an accounting trick. And I have always said that if you include the black hole interior, then the state is pure. So the information problem only arises when you don't have access to the interior. So this is what they would say. But it turns out that this is not a trick, but it's more like an oracle. These formulas that we just presented as conjectures can be actually derived from the gravitational path integral. So we can derive that formula for the fine-grained entropy, sometimes also called Rutaganagi formula, and directly from the gravitational integral. And I would call it an oracle because it gives us the true fine-grained entropy of the exact state, but only using the semi-classical state, the semi-classical approximation. So let me just briefly talk about the derivation of this formula. So it's conceptually similar to the derivation of the black hole entropy formula using the Euclidean black hole. So it's similar to what we discussed for the Euclidean black hole. I think I'm short on time, so I will not discuss it in detail. Well, maybe I won't discuss it in detail. And so the new aspect that arises when you consider the radiation, well, maybe I should discuss a few things. So you can view the Euclidean black hole as computing a certain density matrix by doing the gravitational path integral and slightly open it up here. If we close it, we compute the trace of the density matrix. And we can compute traces of the density matrix to powers by considering the same thing that we had here. And then we connect 3 of them together, for example. Then we get to the cube to the power 3 here. And then we fill it in some way. And we can do this for all possible powers and then analytically continue in the power. And by doing that, well, I'm not showing you the details, but you can believe me, but that by doing that, you can derive this formula. When you analytically continue these powers n from integer n to n very close to 1, you can get this type of formula. There is a similar story for just the black hole itself, where by changing the size of the circle, so the entropy is the derivative of the free energy with respect to the size of the circle. So by changing the size of the circle, you get the contribution which only comes from the horizon. Here is similar. The contribution only comes from this extremal surface. Now, in the case that we are computing the entropy of radiation, the idea is that we are calculating that state by using a gravitational path integral. And when we compute the entropy, we should allow the geometry in the interior of the black hole to be connected in various possible ways, because we are in principle in a quantum theory, in a theory of gravity, we're supposed to sum over all possible geometries, and we should allow different topologies that connect the black hole interiors. And these geometries with the interiors connected, they are sometimes called replica wormholes, because we are computing the entropy using this so-called replica trick, where we replicate the density matrix many times. And this leads to the formulas we've seen before. And in this way, we can find that formula. OK. Now, so far, we talked about the entropy, but what is this telling us about the interior? So let me make a few brief remarks about the interior. So that central dogma only talks about the degrees of freedom that describe the black hole from the outside. And one question one can have is whether the whole interior is described by these degrees of freedom, or maybe none of the interior, or maybe only part of the interior. And the correct answer is that only part of the interior. But to find that part, we'll define a new concept called the entanglement wedge, which is the causal domain of dependence of the region that appear in the computation of the entropy. And this was done by various people, including Mark van Ransdorp in the audience. And so in other words, suppose we are computing, so the entanglement wedge is, I'm just going to give you some examples. So imagine we look at the black hole at time t, right? And when we compute the fine-grained entropy, we have the situation where the minimal area is here at r equal to 0. Then we have a surface that goes from t to r equal to 0. And then we look at all the points whose evolution we can determine from initial data on this surface. All those points form this region that looks like a wedge, and that's why it's called entanglement wedge. Maybe it should be called entropy wedge, but I didn't choose the name. Okay, so that's just the definition of this concept. In the cases where the surface was just behind the horizon, it's something a little smaller. Okay, and there is a similar concept we can define for the radiation. So when we compute the radiation, there is the so-called entanglement wedge of the radiation. And in the case that we have these so-called islands, whenever we compute the entropy of radiation and we include this region in the radiation as part of the computation of the entropy of the radiation, then we are saying that the entanglement wedge of the radiation region also includes a piece of the black hole interior. Okay, and so on. Now, the answer to that question of which region we describe is that the quantum system describes everything that is included in the entanglement wedge. And what this means is something somewhat specific that I will not discuss in detail. So, for example, in this situation, the black hole degrees of freedom that were appearing in the central dogma only describe this portion of the black hole interior. Okay, so if you have access from the outside to the black hole degrees of freedom, you will only have access to this portion of the black hole interior. So roughly speaking, a little bit behind the horizon, but not much behind the horizon. If you, on the other hand, have access to the radiation and you can do anything you please with the radiation, so arbitrarily complex operations with the radiation, then you also have access to part of the interior of the black hole. Okay, so that's what this hypothesis is saying. So the idea is that performing very complicated operations on the radiation, we can extract information from the interior. How exactly that this happened? Well, it's a little not fully understood, I would say. But the idea is that the complicated operation creates some sort of wormhole connection that connects it to the interior and pulls out the information from there. I won't discuss this. So in conclusions, we reviewed the gravitational fine-grained entropy formula, and we applied it to the computation of the entropy of radiation and obtained results consistent with unitarity. And an important result is that at late times, most of the interior of the black hole is should be viewed as part of the radiation, as described by the radiation. And it's not part of the black hole degrees of freedom that were appearing in that central dogma discussion. Now, you can wonder what was Hawking's mistake. Why did he get a rise in entropy as opposed to the one given by unitarity? And the answer is that he was not using this fine-grained gravitational entropy formula. Of course, we cannot blame him for that because this formula wasn't known at the time, but that's what we would say now. And a lot of what we discussed was derived by thinking about aspects of ADS-CFT, which itself involves string theory. But for understanding and discussing these formulas, you only need gravity as an effective field theory. So you don't need anything beyond what you normally use to describe black holes and quantum fields in the presence of black holes. And there is an amazingly deep connection between gravity and quantum mechanics that makes these formulas work. Now, you can wonder whether this means that the information puzzle is solved. And one aspect, which was computing the entropy, yes, it's solved in the sense that we have some way of computing the entropy using gravity, which agrees with what we expect from unitarity. But there are other aspects which are not solved. These formulas, as nice as they are in computing the entropy, do not tell us other things. In particular, they do not tell us what the state of the black hole is. They do not allow us to compute what the state of the Hawking radiation is in detail. They do not allow us to compute the black hole S matrix. So what state comes out when we form the black hole? Conceptually, they are rather similar. These formulas are rather similar to the formulas that compute the black hole entropy. So the formulas for black hole entropy, due to Bekenstein, for example, they were known before we could account them precisely using some microstates or string theory and so on. And so it is a bit like an oracle. It's an accounting oracle that gravity gives us. It gives us the formula for the entropy, and with results which are all consistent with this interpretation in terms of quantum states. But these formulas do not tell us exactly what the quantum state is. Now, what would we want to do in the future? Well, fully resolve the information paradox is one of them, but that includes understanding the singularity in the interior. And I think understanding the black hole singularity is, at least for me, one of the main motivations for studying black holes, because this singularity is very similar to the singularity that we have in the beginning of time. And so if we understand the black hole singularity, hopefully we'll understand the cosmological singularity and understand some aspects of cosmology that we might perhaps eventually test. Thank you.
Great, thanks, Juan.